Okay, folks, here's lesson 20, polynomial equations. Remember, with the word equations, that means we're dealing with an equal sign, so we're finding x values. Hint, hint, we're going to be using set notation for a lot of our answers. Let's get started. The zero product property states that if I have factors of a times b and they both multiply to 0, then either factor a must equal 0 or factor b must equal 0. Let's see this in actual use. Going on to example 1a. Solve using the zero product property. Reminding myself that the ZPP states if I have a factor a times a factor b, they multiply to 0, then either a has to equal 0 or b has to equal 0. So, using this idea, notice that I have factor 1, x minus 3, and factor 2, 2x plus 5. They both are multiplying each other, and they equal 0. So if I apply my zero product property, then I would realize that x minus 3 must equal 0, or we have 2x minus 5 is equal to 0. When I solve these, I can simply use basic solving, so isolate the x, so x is equal to 3, or 2x equals 5, so x equals 5 halves. Now again, as I stated in the beginning, we're dealing with some x values, so we have to remember that this is a set notation. We have 5 halves, comma, 3. On to example 2. Small edit to the problem, as I copied it incorrectly. Let's look at it. We have multiple terms here, not just two. We have 4x, that's one term. We have x squared plus 16, a sum of squares, which is not factorable yet. We then have 3x plus 7, and we have x squared minus 6x plus 8. Could I factor any of those further? Yes, you're screaming it, I hear you. It's yes, we can, the last one. So we have 4x times x squared plus 16 times 3x plus 7 times x minus 2 times x plus 4 equals 0. Now from here, applying the zero product property states that I'm going to take all of these factors, 1, 2, 3, 4, 5 terms, and I'm going to set them all equal to 0. Once I do that, I'm going to solve each equation for the x value. Here we go. So 4x is equal to 0 when x is equal to 0. X squared plus 16 equals 0 when x squared equals negative 16. Now, to solve this, wouldn't I have to then square root both sides? Well, I square root x squared and I'd get x equals the plus or minus of the square root of negative 16. At this moment, we would say that that doesn't exist. However, I'm going to give us a preview of lesson 22, which states that that is actually x is equal to plus or minus I square root of 16, because I is the square root of negative 1, and that means that I have x equals the plus or minus of 4i. Again, that's a little advanced. If you stopped at the blue, you're totally fine for now. The next one we would do is we have 3x plus 7 equals 0. So we would have 3x is equal to negative 7, and x is equal to negative 7/3. Almost last, we have x minus 2 is equal to 0 when x equals positive 2. And we have x plus 4. That's a minus 4, isn't it? I factored a little incorrectly. Let's fix that. That's a minus 4. Because negative times negative is a positive. Good, good. Weissmuller checking her work. So then that makes this a beautiful minus 4 equals 0. And from there, x is equal to 4. Now our final answer should be written from least to greatest. So here we go. We have the set of values that this would make a 0 statement from negative 7/3, 0, 2, 4, and I'm going to put plus or minus 4i at the end since that's the new number. On to the next example, we have 2a. Continue solving using the zero product property. Now what you need to notice on this is it does not equal 0. So remember the ZPP states that we're going to have factor A times factor B, and they have to equal 0. So let's write this in terms of equal 0. That's our first step. So we have 2x squared minus 5x minus 7 equals 0. Now notice that this is not factored form. So what do we have to do? Oh, that's right, factor. We're applying what we previously learned in lesson 19 to this lesson. So we have a beautiful 2x times an x, and what multiplies, right, this is off to the side work, what multiplies to negative 14 that adds together to negative 5. Give you a few seconds to think about that. Hopefully you say that it's negative 7 and positive 2. And then you ask yourself, okay, so 2x times which one of those is divisible by 2? Well, that's 2. 2 times what is 2? Well, that's positive 1. So then this next term, this one here, is what times 1 is negative 7. Well, hopefully you're claiming that's negative 7. Now going back to the statement mathematical that we have to bring down equals 0. Now this does apply to our zero product property. We have two factors that are they're multiplying together to equal the number 0. So therefore I can say that 2x minus 7 is equal to 0, or x plus 1 is equal to 0. Again, we're going to solve for x, isolating your x first by subtracting or adding if necessary, and then dividing last step if necessary. Remember, your final answer is in set notation from least to greatest, so we have negative 1, positive 7 halves, and we're moving on. For example 2b, notice that we have this beautiful, again, equation. So remind yourself, the zero product property states that I need to have a factor of A times a factor of B to equal the number of 0. And if I do, then I can create that A must equal 0 or B must equal 0. But again, I don't have this equaling 0. So step 1, move it all to one side so I can create an equation that looks similar to my zero product property. From here, then I start factoring, and I say, okay, what do these terms have in common? Well, I know 25 is a perfect square, and I know 49 is a perfect square, but I can't break x cubed and x into perfect squares. There's a GCF. So if I think about that, the GCF of those two terms is x. Let me factor an x out. I'm left with 25x squared minus 49 equals 0. Now from here, can I factor what's on the inside? That would be known as that's right, difference of squares in here. So that's my DOS. Remember, your DOS formula states that if you have a difference of squares, you can claim that a squared minus b squared factors to a minus b times a plus b. So let's rewrite it in terms of something squared. I have x times 5x squared minus 7 squared equals 0. So then my factored form of that would be 5x minus 7 times 5x plus 7 equals 0. Now from this step, we can apply our zero product property to each of the terms, noticing that there are 3 terms, right? Or we're back up to 3 terms, 1, 2, 3, and I have to equal them all to 0. X equals 0. Or 5x minus 7 equals 0, or 5x plus 7 equals 0. Now again, solve for x, so we have 5x is equal to 7, or x is equal to 7/5, and 5x is equal to negative 7, or x is equal to negative 7/5. So again, my final answer in my notation of set notation is negative 7/5, 0, 7/5. Close your set. Under example 2c, 2c, we have x to the 4th plus 9 equals 10x squared. Again, reminding ourselves that the zero product property states that I have to have a factor of a times a factor of b, and they equal 0 when multiplied. If that's true, then a must equal 0, or b must equal 0. So let's make it equal 0. Step 1, make it equal 0. We have x squared. Nope, just kidding. X to the 4th minus 10x squared plus 9 equals 0. Now from here, we want to let u, right? I don't like x squared and x to the fourth, so I'm going to let u equal x squared. When I do that, I then have u squared minus 10u plus 9 equals 0. And I can factor that by saying, okay, what multiplies to positive 9 that adds to negative 10? Well, isn't that negative 9 and negative 1? So u minus 9 and u minus 1 equals 0. But I didn't start with u, I started with x squared. So I have x squared minus 9 times x squared minus 1 equals 0. Oh, but what do you notice about these two things? You should be saying it super loud. Do you see a difference of squares on both of them? On both of them, two difference of squares. So let's factor that. We got x minus 3 times x plus 3 times x minus 1 times x plus 1 equals 0. So that means that all of those terms would equal 0. So I have x minus 3 equals 0, x plus 3 equals 0, x minus 1 equals 0, and x plus 1 equals 0. Solve for x in all cases. So x is either equal to 3, x is equal to negative 3, x is equal to 1, x is equal to negative 1. So let's write our final answer in set notation off to the side. And we have negative 3 comma negative 1, 1, 3, close your set. Moving on to example 2D. For example 2D, we have x minus 6 quantity squared equals x. Now again, if we're solving using the zero product property, what do we need to remember? Well, we should have factored form of two things multiplying together to equal 0. If that's the case, then a is equal to 0 or b is equal to 0. So let's rewrite this so that first step, they equal 0. So we have the quantity of x minus 6 squared minus x equals 0. But notice that there's a subtraction symbol in between these two terms. My goal is to have a factoring multiplication of two things or multiple things. And I don't have that. So I'm going to have to expand the first binomial to make a trinomial. So let's do that. We have x squared minus 12x plus 36 minus x equals 0. From there, that makes x squared minus 13x plus 36 equals 0. And then let's factor that. So off to the side, I'm going to do my little x method. I have what two numbers are going to multiply to positive 36 that add together to negative 13? Do you agree that that's negative 9, negative 4? So from here, I can then factor back what I had, and I can say that that's x minus 9 times x minus 4, and that equals 0. By applying the zero product property, I can then claim that x minus 9 is equal to 0, or x minus 4 is equal to 0. Therefore, x is equal to 9, or x is equal to 4. My final answer in set notation is 4, 9. Okay, folks, last one of this set. So we have example 2E. When we think of this one, we want to solve using the zero product property. It says the quantity of x squared minus 3x minus 18 is squared, and that equals 0. I want you to note off to the side that if I have a binomial raised to some power of x, it does not equal the distribution of the power x to my terms. So what I'm hinting at is please do not distribute a squared to all of these terms inside our parenthesis. Rather, that means that we would take both sets of values, right? And we would say, well, this is really like saying x squared minus 3x minus 18 times x squared minus 3x minus 18 equals 0. From here, can I then factor the inside trinomial? So we have off to the side what multiplies to negative 18 that adds together to negative 3. Yep, that's right, negative 6, positive 3. So let's factor appropriately. We have x minus 6 times x plus 3, x minus 6 times x plus 3, and they both equal 0. I'm going to rewrite this so that I can see it in terms of x minus 6 squared times x plus 3 squared equals 0. Now the interesting fact here is that once I have a factor squared and a factor squared, I can say that the ZPP does state that if I have a factor and another factor and they're multiplying together to give me 0, then I can take the factor of A and equate it to 0 and take the factor of B and equate it to 0. Let's do that then. So that means that I have x minus 6 quantity squared equals 0 when, and x minus 3, plus 3, squared equals 0 when. Well, now if I see this squared, what this means is this is called a double root. I'm going to write that off to the side. This is known as a double root. Why? Well, because there's a squared here. It means that that factor happened twice. So to get rid of the squared, do you agree I would square root both sides? Now what's the square root of 0? Well, plus or minus 0, right? X minus 6 quantity squared, and the square root this side of x plus 3 quantity squared equals the plus or minus of the square root of 0. But we know that 0 does not have a plus or minus because 0 is a neutral number, so we have x minus 6 is equal to 0, and x plus 3 is equal to 0. Solve for x appropriately, so we have x is equal to 6, x is equal to negative 3, but what we know is that 6 is actually a double root. So what we can claim in our set notation is we have negative 3, and we can put in parentheses double root, and 6 we can put in parentheses double root. If you see this on the homework key, again, that's because that factor occurred twice. Now let's extend that. If the factor occurred 3 times, meaning it was x minus 6 cubed, well then we'd have what's known as a triple root. We'll talk more about that during our polynomial section, but I just wanted to bring that up. So moving on to example 3, it says find all the zeros of the function. In order to find all the zeros of the function, now remember zeros is the same thing as x-intercept, it's the same thing as solution. Oh no, it's not going to let me type that. Okay, hold on. S-O-L-U-T-I-O-N, I got it. It's also the same thing as a root of a quadratic. Those are all the same words. So we have x-intercept, solution, and root. Now to do this, I have to set up that zero product property. Again, I'm not ignoring that for the whole lesson. I'm using it all the way through. So we have two factors that are going to multiply together to give me 0. But right now they're not multiplying. I have a minus sign. So what I'm going to have to do is factor. So we have to find the zeros. Now notice I'm going to equal it to 0. So I have 0 is equal to, let's factor this, x plus 2 is the common term of x plus 2 squared minus 16. Well, notice this is a difference of squares. So we have 0 is equal to x plus 2 times x plus 2 minus 4, right? Because that's the square root of 16. Or x plus 2 plus 4. From here, let's simplify that. 0 is equal to x plus 2 times x minus 2, or when I add this, I get x plus 6. From here, I can use my zero product property since it says find all the zeros of the function, and I can find my x-intercepts, which means I say x plus 2 is equal to 0, x minus 2 is equal to 0, and x plus 6 is equal to 0. From here, solve accordingly. So x is equal to negative 2, x is equal to positive 2, or x is equal to negative 6. From here, we want to use our answers in set notation, least to greatest, negative 6, negative 2, positive 2, and we're done. On to the next example. Solve for x in terms of a. So when I look at this, it looks kind of nasty, right? But it's a 4-term polynomial, so I want to say to myself, okay, should I factor by grouping in terms of 2 to 2 or 3 to 1? Well, I don't see any perfect square trinomials in here, so I'm going to guess it's going to be a 2 to 2 factoring situation. So let's find the GCF of the first 2 terms. I see there's an x in there. Let's factor it out. So I'm left with x squared minus a squared. Ooh, that's looking pretty. And then on my second set, I'm going to factor out, well, what's in common? I again see a 2, but I want a negative 2 to pull out. Let's look at that y. When I pull the negative 2 from both of those terms, then it becomes x squared minus a squared, and then those 2 factors match, which is what I wanted. Now from here, keep factoring, so we have x minus 2 times x squared minus a squared equals 0. But I would like to then continue to factor the second set because, again, this is another difference of squares. When I do that, I get x minus 2 times x minus a times x plus a is all equaled to 0. And from here, I can use my ZPP, the zero product property, which claims that if I have factors of a and b multiplying together to equal 0, then either a is equal to 0 or b is equal to 0. When doing that, I have x minus 2 equals 0, x minus a equals 0, x plus a equals 0, solve for x. So x is either equal to 2, x is equal to a, or x is equal to negative a. Let's write our answers in set notation, and because I don't know the value of a, I'm simply going to put 2, comma, plus or minus a. On to the next example. Last one of the lesson. It's going to have 3 parts, so we're going to sketch the graph for f of x equals x squared minus 2x minus 8. And we want to use the graph to then solve this. So we're going to have to graph it. Now, when I graph a quadratic, one thing I want to remember is I can always graph the x-intercept. So if I factor this beautiful equation, and I say, okay, what multiplies to negative 8 that adds to negative 2, I think you'll say that that's x minus 4 times x plus 2 equals 0. Now, using my zero product property, well, x minus 4 must equal 0 when x is equal to 4, or x plus 2 is equal to 0 when x is equal to negative 2. So then I can go to my graph and I can say, okay, when x is equal to negative 2, I have this new dot there. And when x is equal to positive 4, I have this 0 here. The last thing you may remember from Algebra 1 is that the c value is always your y-intercept. So I have this to then graph. So then from here, I can say, okay, well, let me just sketch it, right? It doesn't say that I have to graph it perfectly, so let me sketch this graph. And I have something that's going to look like this. Now the question is when does this graph equal 0 for the y value? So let me highlight the y value to help us see this. Here's the y value right there. And where is the graph crossing that line of y is equal to 0? Well, you may be like, well, Ms. Weismuller, that's what we graphed at the original statement. That value of 2, negative 2, and the value of 4. And that's correct. That is what it is. Okay, so our final answer on this one would be that the x values that make this quadratic equal to 0 are negative 2 and positive 4. So then we hit this type of question. Looks the same. We're dealing with the same exact factored form. So what we can do is we can claim that we already know the factors. It's going to be x minus 4 times x plus 2. But now we have to deal with this inequality, and this is where this problem changes. It doesn't say where is it equal to 0. It says where is it less than 0. So I'm going to graph it just like I did on the previous slide. We have negative 2, positive 4. We know the y-intercept's at negative 8. We can sketch our beautiful quadratic. And then I'm going to draw that y equals 0 line one more time. But what I'm asking is where is this function less than 0? Well, you may say that it's less than 0 around here. And you'd be correct. So how do we write that answer? Well, that's going to be interval notation from negative 2 positive 4. Last but not least, we have this last equation. This equation states that we're asking where is the function greater than 0. So what we want to do is, again, state the factored form of it. We have x minus 4, x plus 2, and we're asking where are these greater than 0. So again, identifying those zeros is really helpful. So I can put that's at negative 2, that's at positive 4, we're at 8. I have my quadratic, let me graph it. And then again, where is it greater than 0? Well, that's going to be this section of my graph. So if I look at that, that's going to be from negative infinity to negative 2, or 4 to infinity. Folks, there is something called a sign test, S-I-G-N test, and I'm going to post a separate video about how to use this for quadratic inequalities. That's the lesson for lesson 20. Have a great day.